The most relevant character of the times we live in historic terms, is the rapid technological progress taking place all over the world. Its most immediate result, in energy terms, is an increase in the demand for crude oil-derived fuels, especially distillates, such as gas oils, diesel, motor spirit, and aviation spirit, as sources of energy. Increased industrialization round the world means further increases in the demand for distillate fuels obtained from a finite resource. The suppliers of these fuels meet the demand for more distillates by applying more efficient secondary conversion refinery techniques, such as thermal and catalytic cracking, by which they convert a greater proportion of the crude oil into lighter hydrocarbon distillates. The demand for more distillates thus inevitably results in a change in the quality of residual oils that are available for blending into marine bunker fuels. Effective fuel preparation has always been an essential requirement when burning fuel oil in diesel engines of motor ships. Changes in residual fuel quality create the need for even greater attention to be paid to this important area of responsibility for marine engineers. This is a major contributing factor to cost-effective ship operation in the future. Therefore, this film will deal with the handling and cleaning of residual fuels. Much has been said about the quality of marine fuel oil, which has raised doubt in the minds of marine engineers. Yet, there is no aspect of fuel oil quality which need cause undue concern, providing that the correct fuel is chosen in relation to the design of the ship and the engine, and that the correct handling and treatment procedures are carried out on board. The residues that make up the blended marine bunkers come from several refinery processes. In the first instance, the crude oil is heated and fed into the atmospheric distillation column, where the lighter hydrocarbon molecules are distilled off as gases, gasoline, kerosene, and gas oil, leaving about 50% of the crude as residue. Some of this residue is fed into the vacuum distillation column, where it will be further processed to produce vacuum gas oil, waxy distillates, and a residue. This residue can form part of the blend in marine bunkers or can be fed into thermal crackers. Here, under high pressure and temperature, more light hydrocarbon molecules form and are removed as light distillates. Also, the heavy gas oil from the vacuum distillation column may be subjected to catalytic cracking, where, as a result of chemical reaction, yet more light hydrocarbon molecules are formed and separated into even lighter distillate fractions. The residues from all these processes can be blended with a variety of distillates to make up the specified marine bunkers. The procedures for correct handling of bunkers on board should begin even before the ship enters port. All tanks should be prepared so that when receiving new bunkers, these will not be mixed with those already on board. Such planned segregation is strongly recommended for avoiding sediment or so-called incompatibility problems. This is important because while blended fuels are stable as supplied, there is a small risk that some fuels, when mixed together, could produce asphaltic sediment, sometimes referred to as sludge. Knowing the details of the next voyage and the available tank capacities, the engineer can work out the quantity of bunkers to be taken on board and loaded into each tank, making sure that the ship's stability is maintained throughout the bunkering operation.
Right, it's about after four. Stop it, please. Stop, and then stop.
On contact with the supplier's representative, confirm, preferably in writing, the viscosity and quantity of bunkers required, and also whether the delivery is to be shore stop or ship stop, and what delivery rate is required. Find out if the line will be flushed after delivery. The quantity actually delivered will be calculated by the suppliers, whose measurements and calculations may be checked by the chief engineer or his representative. Ensure that all the necessary bunker line valves are open and that those which are not immediately required for use are shut. The fuel will be supplied at a temperature sufficiently high to ensure trouble-free delivery. Make sure that the bunker couplings and lines are free from leakage before delivery is adjusted to full rate. Constantly check quantities during delivery to ensure that each tank will receive only the required amount and that your vessel remains stable. Ensure that you stop delivery in time, allowing space for the flushing oil if the line is going to be flushed after delivery. All bunker valves, which are not in immediate use, must be kept closed. If the bunker line has not been flushed, ensure that it is drained as soon as delivery has finished. In low ambient temperature conditions, after delivery has finished, there might be a risk of the fuel cooling down below pour point, causing blockage in the supply line. It may be necessary to have steam trace heating fitted and adequate insulation provided for these conditions. The supply line can also be mounted at an angle to facilitate self-draining. Witness the final shore or barge measurements and check the quantity received with figures on the delivery receipt. Draw attention to any significant discrepancies immediately. The supplier will not normally consider any shortage complaints after the vessel has sailed. Make sure you receive a representative sealed sample of each delivery. There is now a wide measure of agreement within the industry on the need to supply marine fuel oils against agreed specification limits. The system adopted will refer to a particular fuel oil grade, rather than the old system, which only referred to viscosity. The grade system not only defines the fuel's maximum viscosity, but will also define other important aspects of quality. The quality limits of the grade of fuel ordered will determine the best method of handling and treating the fuel on board. The maximum pour point of modern marine fuel oils is 30 degrees centigrade. Therefore, the bunker storage tanks on board should be capable of being heated and maintained at this level, being lagged wherever possible to cut down heat loss. When transferring bunkers, whether into other storage tanks or into the dirty settling tanks, care should be exercised that the vessel remains stable and that bunkers are segregated where possible. The transfer of bunkers from storage into settling tanks should be done at higher temperature levels, ideally around 50 degrees centigrade, especially with the more viscous fuels, in order to achieve effective pumping and rate of settling. Use low suction at this stage of handling bunkers. Recirculation should be avoided as much as possible in order to avoid the possibility of emulsification due to water contamination. Ideally, the fuel transferred into the dirty settling tanks should be allowed at least 24 hours to settle, and the inlet manifold should be as near to the top of the tank as possible. The fuel here should be heated to a level which will give you an adequate settling rate within the design of the tank, but the temperature should not exceed 50 degrees centigrade. The dirty settling tanks should be fitted with high and low outlets so that high outlets may be used during adverse weather conditions to prevent water carryover. Oil outlets must be filtered, the filters checked, and elements cleaned regularly. Fuel in the dirty settling tanks should be kept at a constant temperature to facilitate easier temperature control of the fuel reaching the cleaning system. The fuel must be checked for water at the water test cock. Great importance is attached to the correct method applied to cleaning today's fuel oils. It should be a cost-effective operation, obtaining the highest possible degree of cleaning. For this reason, the use of a cleaning system based on self-cleaning centrifugal separators operated at a temperature of 98 degrees centigrade is recommended. The heart of the separator is the bowl, which consists of a body and a hood held together by a lock ring. The space within the bowl is occupied by the top disc and a stack of stainless steel conical discs. Separation takes place between the conical discs due to the centrifugal force acting upon the heavier components, such as water and solid particles like rust and catalyst fines, together with solid asphaltic residues, which flow outwards towards the periphery of the bowl. The separator can be operated as either a purifier or as a clarifier. The separator's performance, when operated as a purifier, is based on the position of the interface which forms between oil and water inside the bowl. The space between the interface and the periphery of the bowl acts as a holding space for the sludge until it is removed. This space is filled with water to form a seal for the oil, and in order to achieve a good cleaning performance, the interface must be in its correct position, that is, outside the disc stack and as close as possible to the outer edge of the top disc. The interface will move into the disc stack if density or viscosity and the flow rate reduces, and also if the temperature of the oil rises. A broken water seal will result if the density, viscosity and flow rate rises, or if the temperature falls. The correct position of the interface is achieved by using the correct gravity disk for a given density, viscosity and flow rate. The diagrams in the manufacturer's manual indicate which disk should be used initially, but final selection of the optimum disk is best determined after each bunkering by trial and error. The correct gravity disk is the one with the largest inner diameter, which does not cause a broken water seal. The effective operation of the separator then depends on the rigorous maintenance of a constant flow rate and temperature of the oil. The recommended system for cleaning today's fuel oils consists of two separators connected in series, one set up as a purifier, the other as a clarifier. By varying the arrangement of the bowl parts, the separator can be made to function as a purifier or as a clarifier. The separator, when working as a purifier, has two liquid discharge ports, one for the clean oil, one for the water. The gravity disc is situated in the water outlet port and controls the water outlet. If the separator is set up as a clarifier, the water outlet is not required and is blanked off, so that only the oil outlet functions normally. If a small amount of water remains in the oil after passing through the first separator, it is ejected with the sludge from the clarifier on desludging. This additional feature is of great value, as the cleaning of today's heavy fuel oils means operating near the limits of the capabilities of centrifugal separators. The separator throughout should therefore be controlled to closely match engine demand. As an integral part of the recommended system, 2 separate positive displacement pumps, situated as near to the settling tank as possible, should be used to feed the cleaning system. They should be connected in parallel, one working and one on standby. When treating fuel oils of 380 centistokes at 50 degrees centigrade viscosity or less, the separator should be discharged or adjusted to discharge sludge at least every 1 to 2 hours. Since the standby separator is now recommended for use as a clarifier, a regular maintenance schedule for the separators should be implemented to ensure the continuous, efficient operation of the cleaning system. Sludge disposal has always been a problem at sea. There have been many solutions found, some desirable, some less so. But sludge should never be discharged overboard. It pays to remember that sludge contains combustible fuel, which can be cost-effectively used to supplement the fuel in a boiler. One important point needs to be kept in mind. The system must be capable of being heated to maintain sludge at above the pour point. Up to now, we've been concerned with the handling and treatment of dirty fuel. Here we can see the clean fuel system, where the problems are very different and center around the correct viscosity and temperature control of the fuel. Contamination of the fuel by water can still occur, either as a result of condensation or from a leaking heating coil. The surcharge pump feeds fuel for distribution to all the main engine fuel pumps via the fuel heater through the fuel rail. The main engine fuel heater will heat the oil to the required temperature in line with the manufacturer's recommendation to ensure that the fuel viscosity is exactly as required at the engine fuel inlet. We recommend that the temperature here is controlled by a viscometer. The fuel delivered will be in excess of the engine requirement. This excess has to be returned to the system. The oil here is well above flash point, therefore it should not be returned direct to the fuel tank. It is recommended that this spillback is fed into the suction side of the surcharge pump. To help maintain the required temperature levels, the fuel line should be lagged right through to the engine fuel valves to cut down heat loss. The filters on the fuel oil delivery system must be capable of providing adequate protection to the engine fuel pumps and fuel valves from any scale, carbon buildup, or other abrasive particles detached from inside the fuel lines. Viscometer, thermostats, and filters must be checked regularly for correct operation. Problems with onboard fuel handling are not uncommon for marine engineers. Most of you will have a lot of experience and found solutions. This film is intended to help you with your own solutions and to provide ideas for alternatives. The specific aim is to improve the safety and effectiveness of your fuel handling system. In summary, the main points of marine bunkers handling are: 1. Planned use of bunker tank capacity to segregate bunkers. 2. Ensure adequate heating for bunker storage tanks and transfer lines. 3. Drain transfer lines where possible between each transfer of bunkers, ensuring that valves which are not in immediate use are kept closed. 4. Operate centrifugal separator in series, applying constant flow rate at a constant separation temperature. 5. Do not allow storage system temperatures to fall below the pour point or exceed 50 degrees centigrade. 6. Operate strict maintenance schedule for separators. 7. Maintain an efficient sludge disposal or utilization system. Next, the main points of clean fuel handling. 1. Maintain accurate temperature and viscosity control. And lastly, maintain filtering efficiency by cleaning filters regularly. These recommended principles of fuel handling and treatment will help to ensure that the machinery in your vessel will operate at optimum efficiency.